Good evening, everyone, and I'd like to introduce you to Alex Cotterill and Jordon Panayi, beg your pardon, both from Groupwork, which is led by Amin Taha. And just to say, I went to go and have a look at, there's a project in Earls Court called the Stone Demonstrator project. Earls Court Station, very easy, just get to Edgware Road, change. Warwick Road entrance, walk across the back of the site. Anyway, it's a really nice, as it says, demonstrator of how you can build with stone, and you see the details. It was semi-fenced off the other day, but it's open now. And just go and have a look, because some of the principles I'm guessing we'll be talking about this evening about a project in the Finchley Road. They're sort of shown there, and they're very diagrammatically and very clearly visible, so you kind of understand the logic of it, because I'm not sure it's always that easy to understand without that as a diagram. So anyway, it's really nice that you could join us tonight, and thank you for going around rallying the troops, and thank you. Thanks for coming in. Thank you.
Okay, hi. I'm sorry for those of you who I rudely grabbed and told to come down here. I know what it's like studying, so, don't worry. So we were asked to tell the story of a building we've nearly completed called on Finchley Road. So like all good stories, I'm going to sort of start a bit further back, and then I'll get to that, and then we'll show you some other stuff we've been doing. Also, I appreciate that you've all got super short time here and attention span, so we're going to go through loads and loads of stuff, but very quickly, all right? So you're just going to be like really quite intensely abused with our projects. So just to start here, give some background about why we do what we do, like why we make the decisions we make. This is, I don't know if you've gone through this in your education so far, a breakdown of EN 15978. That's the global standard for how you measure carbon in a building. What you realise that it's split between materials in use and then end of life, and more or less, materials is about 55% of the carbon, in use is about 40%, and then end of life is about 5%. So for us as architects, we were interested in what can we do to these to try and lower these. So with the BSRA and the University of Bath, over the last couple of years, we've put together a list of all the kind of key materials we've been using and just the equivalent amount of embodied carbon they use. So as an indication, at the very top, you're using something like aluminium covered in plastic paint. That's the highest in carbon. And then right at the bottom, in the kind of minus area, is all your timber, your CLT, things like that. Now, what does that look like? So it's as you would imagine. So your concrete blocks, your steel beams, your steel sections, your aluminium plates, things like that. All your layers of material, your rebar in your concrete, all kind of at the top towards the middle, and then down the bottom you get your timbers and your dowel laminated timber and your cross laminated timber and things like that, and then your stone blocks. So that was just interesting to us. We weren't trying to push things one way or another. So if you start at the bottom, a couple of these figures are minus, so you have like a minus amount, so they're actually taking carbon out of the atmosphere. And why is that? It's because when a tree grows, it sucks the CO2 out of the air, takes the carbon and releases the oxygen. So in doing so, through photosynthesis, it's actually capturing the carbon in the atmosphere. So there's a thought experiment that if all the area that you cleared to make way for development, as in chopping down loads of trees for grazing land and things like that, if you put those all back to woodland, we'd be back to pre-industrial levels of carbon in the atmosphere within about 100 years. So that was why those figures, if you go back to this, then become minus, because you're growing timber, you're putting timber back, and that cycle is actually capturing timber. So timber is essentially good. Now on the other side, a bit further up there, you start to notice that stone, sandstone, natural stone, limestone is quite low as well. And why is that? It's because stone is there. It's beneath our feet. And so all you need to do to take it out and process it is just extract it, and then you can put it on a building. Very simple, and we'll get to that in a minute. So then people say, okay, well, if you're going to do that, you're going to run out of stone. It's going to be, acres of the world that's going to be covered in quarries. Whereas this is the largest quarry in Europe, in Belgium. So it does the equivalent of 800,000 three-bedroom houses worth of stone every year, and that's the sort of size of it. And then you think, well, okay, well, if we keep on going, what's going to happen? Well, you don't realize that the crust that we're sitting on, the Earth's crust, this is all stone here. So all we're doing is chipping away parts of this. Underneath that, it's just a boiling ball of magma, essentially. So that will just keep on coming up, forming stone over time. So you're never running out of it. So we thought, okay, well, surely other materials also need quarrying and things like that. So what you realize is that steel, cement, reinforced concrete, the makeup of these materials, they need mining, they need quarrying. So it's not like stone on its own is going to ruin the world with hundreds of quarries. You realize actually cement is made by the limestone. So that's stone taken out, burnt to a high degree, crushed, mixed with all these additional components, put with some rebar, and then it's sort of half the strength of a bit of natural stone. I'm getting all the technical stuff out of the way whilst you're kind of fresh in the room. So our reasoning was essentially all these bits of research. You don't really know what's going to happen when you start research, and you just have to see where it leads you. And then this, as dry as it gets tonight, but this is how we process that in the office. So this is split between our materials, how much carbon we're using in the building itself compared to various standards across the world. What happens after the building is complete. And then you get a figure essentially down the bottom there. So all you do is put the figures in based on your models and things you're making, and it gives you a figure. So you're pushing that as low as possible. That's essentially because when you look at the alternatives of that, then a lot of the construction technologies now are based on layers of materials, and although the final finish is a bit of stone that we're talking about, there's layers of material behind that to do your fireproofing, your waterproofing, your insulation line. And to be honest, there are millions of these kind of companies and these systems that are put in place. All the buildings you'll see around you will be built in this way. And I think as architects, we're just a little bit almost kind of a bit lazy. So all these layers, all these different products you have to go to, these people you have to go to, it's just a bit long-winded. In its most extreme example, then, that's just a sort of figure of a material that's fixed to the building. Now, what happens when that fails is that, this was a building built down the road from our old office. We watched it go up over months, and there's, elements like a bit of timber that has bricks glued to it. And that's because, people like you, graduates coming out, working in these practices, have this model, and they just like press the brick button, and everything turns to brick. Every surface you see turns to brick. And then, okay, let's go and do that. Let's build that. And that means there's layers and layers of structure to hold that brick up. There's areas where that brick has to be, as I say, glued on, held within an inch of its life, just to kind of fit that vision that you've made for it. And then that fails, obviously, times when it just peels away. All these layers that are completely unnecessary fail dramatically. So we wanted to understand, we don't know, or we didn't know, what the alternatives are, because you just don't. And you have to come to these sort of discussions and be taught in this way to find out. So we visited a quarry. This is a limestone quarry in France. And you understand very quickly how the stone is extracted, where it comes out from, because we had no idea. And you talk to stonemasons, the people who are doing it, the people who are cutting it. It's all very basic. They're just people cutting stone, and they'll just tell you how it's done and what it can be used for, and then how much it costs and like how long it takes to get to site and things. So in doing so, yes, there's a practical application of it, but also an interesting story of how this is extracted, what else could be used for. And in the process of extraction, these little elements that will come up and show what the material is. So this is sort of bits of quartz, fossilized ammonite shells, so limestone is sedimentary over many years of sort of millennia. It's formed. So when you split that You get the some areas which are just completely full of drill marks where you're splitting it, and some are bits of fossil. And then as it comes out the quarry, it's just a very simple bit of stone. Very simple. What can you do with it? So the first project we looked at was in Clerkenwell to use this, and this is essentially doing an exoskeleton in stone. So the equivalent type of building would be a concrete frame or a steel frame, so lots of carbon at the top of that list. And our decision was, okay, maybe if we can just make those of solid lumps of stone, does that make any sense? Does that work? Is it cheaper? Is it quicker? Turns out it is on lots of those areas, and all you need to do is figure out the detail. So the detail is very simple. It's like Stonehenge put together, so it's columns and beams sitting on them. And all you got to do is tie that back to your floor plate. And then there's a rain screen that comes behind there, very simple. The thing is that you can leave this exposed because it is just a natural material. It's doing your structure and your finish. And all the decisions you make are how to turn it when it gets onto site. So these additional straps, the sort of fixing boss at the end, this is as simple as we could make it at the time. This is coming up to about 10 years ago. So when it's made, the floors were temporarily propped, all cast, and then the stone started to come in very slowly, piece by piece. So it was delivered to site in just a block like this, slight little cutout in some areas, but the rest of it is just straight out the quarry, craned in, and then dropped into place. So you can see the stonemasons there. The idea of a stonemason, it's not some romantic vision of someone with a sort of hat on and a chisel. It's just anyone, just a builder on site. So this is what we're trying to understand: what's easier for them, what makes sense for the building, craned into place and just dropped in. And at the end, all the decisions are can you rotate that 90 degrees? And then which elements do you want to see? So these are split with a drill. This is just completely split along the seam, the sedimentary layer, and then this is cut with a saw. And then behind there, it's very simply just a curtain wall. So with bits of timber, bits of glass in between where there's windows. So super basic. And then inside it means that all the elements are column free, so you can do whatever you want. There's a building that you can constantly adjust, and people have adjusted it any way they can, essentially. So this is the project we were asked to talk about. This came into the office then after we finished that job in Clerkenwell. So we applied the same principle, just on a series of 3 buildings, 10-storey and 7 stories. This is opposite Finchley Road in Frognall Station. It's just about to finish on site now, so within the next couple of months it'll be all open. The battle we're having at the moment is there's an Asda coming in on the ground floor, so we're trying to get rid of their signage. I'm not prejudiced towards Asda, but it's little battles along the way. So it's formed essentially by three buildings, a larger one, 10 stories, 7 stories, and then a sort of 7-ish, but half in the basement at the back, and then that's split with a core in the middle. So it's a sort of maybe Richard Rogers way of approaching a project where you have a sort of separate circulation core, and then your buildings rotate around that, a sort of knuckle in the middle. And then you can see on each one, instead of those being tied together with a core, they're just individual buildings. So they want to sway around because they're just a frame. So there's a couple of walls in there that are structural as well, but the rest of the structure is, or the principal structure is just the external exoskeleton. And in the middle, your floor plate, similar to the previous project, just span between. So the stone varies in size depending on the structural duty it has to have as well. So this is a sample that we did in Italy, and this was just to see, first of all, could we get a stone that was that colour, and also can we evolve the fixing detail to make it a bit more simple on site. So essentially, this is a massive bit of steel, about 0.5 meters high, and that fixes into the floor plate, you can see here, and then the stone just slots in both sides. All these holes are just for mortar to come through and then for you to drill it in. So again, although it looks like there's many layers in here, it's as simple as you can possibly make it for that type, and then it's just insulated behind, and that's your floor plate. So it's coming onto site. It came onto site a couple of years ago now. It's been delayed and delayed and delayed, and then now it's nearing completion. So we have the block at the back. This is the 10-story block at the front, and this is the side block, and this is the core in the middle that's going to be finished in the next couple of weeks with the sort of mesh that goes between it. Now the stone supply changed as we were on site. So there's some of it is basalt, and some of it is granite, and that was sourced from Italy for the basalt, and granite was from Norway. And it's a building that's over 18 meters, so the fire protection had to be a bit higher. So obviously limestone just explodes if you heat it up. Basalt was obviously from a volcano, so it's fireproof. And then granite is very, very dense, very, very hard, so that you can use that for tall buildings as well. And then there's a couple of bracing members here you can see. And that's because, as I said before, it kind of wants to twist if it's on its own. So you just need to brace it every now and again. And it acts as a sort of a couple of shear walls in the middle, and it stops the sway frame from swaying. If you start to approach the building, there's a complete variation of the stone finish. A couple of the blocks have just been left as they were exported from the quarry. A couple have been left as they were split. And then a couple we decided to let the stonemasons carve into. So they went with this sort of like a Celtic pattern that's linked to some history of the area. But essentially it's simpler than Clerkenwell. The stone is much more flat because of the nature of it. And the amount of finishes is also fairly restricted. Now, the amount of finishes being restricted, that's purely just because of how it's coming out the quarry, like the kind of quarry we're going to and stuff, having a bigger building. So there's a slight issue in stone that they won't secure you all your stone before you start building, because they might get to a bit in their quarry because they don't know what's down there. So they're literally quarrying as you go, and they might hit a spot where they can't use the type of stone, because these are single members. So this is the fixing bit that I was saying. So that's back into the floor plate. There's a couple of bolts in there, and then the stone column sits on the bottom and the top, and then your beams just are grouted into there. And then there's a bit of the back which is filled with mortar to fireproof it, so the fire can't burn all that steel plate. And then this is a bit of a close-up on some of the areas that they've started working into. And that's another one. The core is then I went through a couple of different iterations. So how it was settled, these essentially are large blocks of granite. So that's 12 centimeters thick by about 3 meters tall, and then they're split at about 1.5 meters wide, and they're just craned into place. Big blocks. So you can do that for any of your internal wall build-ups or external, and then these are made from blocks. So this is stone blocks replacing what would essentially be concrete blocks, and there's some slightly bigger lintels here that transfer between where you have doors and vents and things like that. So what we're trying to do is use stone in different ways throughout that. So it's either these huge blocks that are, again, craned in like slabs vertically to form a lift shaft, and then just mortared together. That went up in about 3 days, that whole thing in the middle, really, really quick. Or at the back, and just trying to replace what would otherwise be concrete or anything else. So this otherwise would have been a concrete core and a concrete shaft at the back. So it's trying to explore different ways and different products from stone that we'll get onto in a minute. So this is a close-up of the stone blocks we're using there. That's from Norway. It's another type of granite. Again, it's like split. It's very, very cheap. Split into 12 by 15 centimeter blocks, and they're just arranged like a bricklayer would do it. Very, very simple. We're not interested in anything specialist. We want to have it as accessible and minimal working as possible. And then that's it going back into the core. So then all the stairs surrounding that are all just perforated steel plates that span from the outside wall onto this core there. So again, very simple palette of materials, just doing what it needs to do, and that gives you a bit of slip resistance, which is good because none of the water sits on it, it comes through, and then everything is as minimal as we can. And then you go through all this effort, and then it gets passed on to someone else on site, and there's a sort of festival of skirting boards that pop up, and these sort of things happen. So although you go through this hard work and like have the opportunity to speak to people about it, still someone is waiting there just to kind of like screw you over. So that got us previously, like I said, that started on site probably about 6 years ago. And at the time we were looking at big blocks of stone, huge column, 2.5 meters high, big beams and things. Now the issue with that is that you need to find a bit of the quarry that's perfect and a bit of stone that's perfect, no cracks. And that's actually very difficult to do that, and you end up with lots of waste, and that waste is fine for the quarry master. He'll just sell it to be crushed for something else. And we start asking, well, can we use that? So this is just finished. Will was just saying about it. This is the project he's talking about on site in Earls Court. And it's essentially a pavilion, a way to demonstrate lots of different ways of using stone. So if any of you are looking at using a bit of stone in your project, then I would say this is a good starting point. This is sort of like summary of everything. So just take you through it really quickly. The principle of this is there's a frame. So this is good for buildings that are built in a frame, a sort of steel frame or concrete frame, a replacement of that. This is also good for tall buildings as well. And the way these are put together is blocks. So blocks of stone, small blocks, 0.5 meter tall or so, and then they're drilled, and a cable is run between them, and then they're post-tensioned. So a bit like a kebab, a shish kebab, you put the cable through the middle and you tension both sides. So you can do a model quite easily. Our students do this, and you tighten up both ends and it creates a beam. Or if you loosen it, it just all falls apart. So that's the way the beams are put together, and that means that you can actually use all these smaller waste bits of stone. So it's much, much cheaper, much better. And the same for the columns. And then they're just joined at the end with a one steel sort of fixing plate that accepts that end and this end and that end. So it's trying to minimize that and be as expressive as possible in this instance. The floors are then a series of different types. So the top is dowel laminated timber. So I don't know if you've looked at it yet, but cross-laminated timber is obviously in different directions and it's glued together. Obviously the glue is bad. So we were looking at companies in Slovenia who do dowel laminated. So it's basically the same thing, but they put a hardwood dowel in between to lock the whole panel together. And that dowel then expands and does exactly the same job as a CLT panel, but it's all timber, so there's no glue whatsoever. Much better. The middle one is timber joists with then stone slabs drilled into the top. And that's good because timber wants to bend, but stone is very stiff. So if you combine them together, you can have half the amount of timber and stone because they're sort of working together in one beam. So stone's good in compression, but timber's good for bending. So it wants to bend, but the stone can't compress. And you can also use it as your floor finish. So you can just walk on it. It's done, very easy. And these are floors made in the same way of these. So just thin panels spanning from side to side. And there's just two bolts in the end. And on the outside, these are stone blocks. Well, these are all stone bricks, basically, cut into block sizes or brick sizes. Same price as a brick, it's just they're sort of 90% less of the carbon. So it's like a sort of no-brainer, really. You get them in all the colours you would want. So but you get a bit of interesting texture because they're coming straight from the quarry. This is just a zoom in of the beam here. We've used different types of stones, so some limestone, some granite, just to give you an idea that there is variety. And this is the underside of this slab. As you can see again, you can just keep that completely exposed. And this is the timber and the stone slab there. And then just for argument's sake, we put in a sort of plasterboard lining to reveal this external skin. So it's just stone lintel, stone sill. It's like you would build, 100 years ago, 500 years ago, but again now, because no people are tentatively getting back to it. So that same approach we've used recently on a project in Albania. This is in Tirana, right in the middle. We're doing quite a lot of work there at the moment. And this is essentially in one single tall building. And you can see that the stone sizes vary quite dramatically, and so does the cross bracing. And because we're architects, we had no idea about how many cross-bracing members you need, so we just went like a plethora all over the facade, so maybe a bit too much, but other than that, it's doing exactly what it needs to do, and then there's stepping where we need to. At ground floor level, then you can see the same sort of technology as before, so these are still acting as beams, but they're essentially walls, the size of a wall, and those are just bolted together into either side, and then your base, again, is just bolted to accept whatever angle you're putting towards. And your cross-bracing you can do in stone as well. So it was combined with some lower buildings. So the lower buildings don't need as much cross-bracing. But again, it's back to that thing that it wants to twist around. The interesting part is that this is adding to the layers of your building, right? So this is adding a bit to the story of your building, why it looks like it does. And then you can see the family together. So this is, in urban design terms, this is like the mother and father, and then the kids in the middle. That's how they normally present it. And we decided to gold plate some of these blocks just for a bit of fun. They like that over there. And then some similar details as we've done elsewhere in Clerkenwell. Okay, I'm going to hand over to Jordan to talk about other bits of stone.
So the project that Alex took you through just then, mainly the Finchley Road and Clerkenwell Close, have been over sort of a decade of work. And so in the background, we've kind of been experimenting, testing, failing. And I'm just going to give you a quick speed run of a few lessons that we've learned along the way. Starting with Graz Bridge. So this was a competition in Austria for a 75-metre bridge. We proposed sort of offered four options. A solid U-channel that's post-tensioned, a fully stone bridge. This was developed with Webb Yates. And then we began cutting holes in this U where the tension wasn't necessary. And each one becomes more refined in its structural performance and rationalizes the material use. And then eventually arriving at a rationalized truss system, fully stone. And then they decided that they didn't want a stone bridge at all. And so we started playing with potentially just having a tensioned top and bottom chord with timber trusses between. And a few of our architects went over to Stone Masonry Company and built some 1-to-5s of this fragments of this bridge that were later displayed in the RA. House in the Woodland. So this was really an estate for the client to sort of play and experiment, and his brief was essentially just to test everything we've learned. And so again, we've begun to have fun with sort of minimalized worked stone, so expressing the extraction from the quarry, and then these post-tensioned beams laid next to one another to form floor plates with the tension rods expressed at each end. And then you really begin to have fun in this semi-subterranean swimming pool that we proposed. Some of the architects worked with the engineers to develop a balloon with threads, which essentially plays with the distribution of ribbed vaults to infill. And these rib vaults were eventually tensioned and then connected with a steel node at the apex so that we could construct them off-site and bring them to site and assemble there. And then these infill pieces, the parts of the balloon that were swollen between the threads, are infilled with these waste stone, laminated waste stone panels, which I'll talk about later. And then in moments where the structure doesn't rely on the infill, you can leave light wells. between the asymmetrical ribbed vaults. Does it work?
I was going to say, we concluded in the office that we went a bit over the top with that project, but it's a good experiment for all of you to play with. So, yeah.
Yeah. So these are the laminated stone waste. They were developed and funded by the Italian government, working with Atelier Romeo. There's Alex sitting on top of one. But essentially, they had a problem with offcuts and producing too much waste, and they wanted to reform them into tiles. And to do that, they sort of laid them out in formwork and binded them with a stone-based resin. And we said, well, you're already laying it over formwork, so you may as well form some sort of structure out of it. And so here, quite simply, they were just laid over truncated cones and then fixed and laid next to one another. And they began to experiment with this, take this further. And so what you're seeing here is the evolution of that with your external faces in the laminated stone that sandwiches in an insulation, which can later on become either a facade panel or a roof panel. And these were eventually displayed in the Seoul Biennale just before COVID. And so here you can see the gaps between the cracked tiles, where the resin reads almost like marble veins. Christ College Library, so this was for the Cambridge campus. Very similar structure, stone piers with inhabitable timber elements slotted between. But what was really interesting with this project was its stone and PV panels that lined the facade to diffuse light into the library. But also, the idea was to use the PV panels to gain enough energy to power the remaining of the college. And so you can see here both negative in embodied carbon and operational carbon, which is due to the PV panels. BEIC, this was in Milan. It was another library, public one, but also an education centre. It's very much the same as Finchley, the post and lintel construction, with this time CLT floor plates. But where openings were larger than 14 metres span, we introduced these large steel columns that then added an accent colour to celebrate these moments, as well as rather than the concrete structure that we had at Finchley, we allowed for some post-tensioned beams that hold up the CLT internally. And then Maxi. So this was quite a nice project for Amin. He started his journey sort of working for Zaha, who designed the original Maxi. So it was nice for him to return in almost a full circle and work with the existing. And so we proposed this here, an extension of the museum. It is meant to be a more secure extension. So we proposed sort of a simple block construction with some more subtle moments of the stringers being exposed, revealing what's happening behind, and some moments of spoiler arriving in the context of the museum. And something close. Quite often we get clients, quantity surveyors and contractors who, from the offset, are quite reluctant to use stone because they deem it as a luxury. So in office, we asked around across the UK quarries and Europe if they could cut stone into the size of a brick, a simple clay brick, and if they can, how much would that one brick cost? And so we were surprised. We've got a huge range of prices back from 65p, which is essentially the same as a clay brick, to some more £1.70 sort of higher budget that's almost like a Zumta finish. And so this is something close, a project that we're working on just down the road from Finchley on the same street, where we're essentially applying what we learned through the Stone Demonstrator and all of these technologies that we've developed since Finchley Road, with a self-supporting stone brick facade, post-tensioned beams internally, and then the CLT floor plates, and then your PV brise-soleil system on the external to power the building. And this is very early on, prior to planning. So, yeah. Besides, in practice, we've been testing our findings across academia too, both with a lot of our staff teaching internationally, but also our Part 1s and 2s going in to finish their education. And I was lucky enough to work on, in very much the same position as you. This is me as a Part 1 working on Finchley Road, signing off the stone sample on a very precariously stacked timber table. I was very lucky enough to be able to see the project develop, both as a Part 1 and Part 2, and now working in the practice again. And inevitably that inflicted in my Part 2 education. So at UCL, I was really interested in this plug and feather method as a sort of quite rudimentary and economy and means of splitting a stone, and how this technology might be brought to more remote or rural areas. So this technology has been since sort of the past 2 millennia as a method of just separating 2 pieces of stone, typically in one axis. You strike the peg that drives 2 steel wedges into the stone and pushes it apart. And so my thesis was essentially testing how this one axis simple method of shaping stone can be brought to 2 and 3 axes to form a minimal energy and minimal waste form of shaping stone. And so you can see here I'm beginning to test these multiple axes of splitting and balancing or choreographing the tolerances that the split make, tied to tolerances around openings and doorways, thresholds, sort of parallel to how you might tailor a suit or a dress. And so it was this attempt to make a tailored architecture for these rural contexts, such as rural Portugal, taking these typical components such as a corner, windowsill, block and upstand, and a nested vault system for a floor junction, and forming them using purely plug and feather. And then you begin to develop some kind of architectural language that could roll out as an affordable housing system. And so that was just my example, but there's many around the world, from America, Harvard, Yale, RCA, and UCA. And I'll pass the microphone back to Alex, who will explore. You've been teaching RCA, right?
Yeah. So we have been teaching for the last sort of 5 or 10 years or so, on and off, and sometimes get invited across to the States to do a sort of semester. So last year it was at the Harvard QSD. Again, exploring exactly the same topics that we've just been talking about, and through a very simple brief is very basic. It was office towers in Earls Court. So the brief doesn't have to be like something that's you've like reinvented the wheel or anything. It's very, very simple, but through like iterative design, we then looked at different forms of playing with these technologies that we've been looking at in practice, through post-tension stone, stone blocks, different forms of that in terms of plans, sections, elevations, and vaulting and things like that. So over time with students, you sort of carry on this research. So I think as students yourselves, it's quite an interesting position to be in, that you're really, as sort of master's level students, you're really that. You're masters. You're pushing the boundary of what everyone's doing in the industry at the moment. It's not just, I'll do the minimum, I'll tick the boxes and get out the other end. So we actually use a lot of student work as part of our research, and then students come to the office to work further on that. And we help them then go through and develop some of these projects further. We teach them regularly a design studio at the RCA, so it's slightly more technical on the first end. So we ask them to copy their like notable buildings around the world, fitting into different categories like housing, towers and things that are all built in concrete, and then redo them in stone and timber, and it's exactly the same, a carbon copy, but in a very low carbon way. So then we help them with those details. They then go on to explore their own projects. So it's again similar sort of either found sort of objects like this student in a sort of slightly unresolved scheme, or things that are a bit more elegant and refined. But again, it's the same sort of interest that the practice has in using low carbon materials to really like tell the story of their project, and also inform, importantly, your architecture, and let that dictate what your building is doing. And then sometimes they look in across the other side of the world and to push the operational side of it as well as the material side of a project. So it's a kind of like, again, it's an interest we have not just in terms of practice, but in terms of academia as well. So that's why we like coming to see other universities. Thank you. That's it. Questions? Shall I ask questions? All right. Go on then. Yeah, there's another one here.
Does this work? Yeah.
Thank you for the lecture. What are some common challenges you're facing when it comes to building with stone and in terms of planning?
Planning as in like planning permission?
Yes.
Nothing in terms of planning permission. They love it. They absolutely love the way that using stone will tell a different story of a building or the area, and it's low in carbon. And it looks, if you want it to, it looks exactly the same, but it's a bit more expressive of what the material is trying to do. So any details you see on these projects, there's a slight ornament to them, and you have to understand that is driven entirely by what that material is trying to do or wanting to do. So if there's an exposed bit of beam end, we're quite happy to let that poke out the facade and make a special moment of it. It's a form of detail, instead of just an applied bit of ornament. So they like that story about it, but and then I guess the struggle after that is trying to convince people that it's a accessible, easy, risk-free way of building. So, I mean, a bit of that is how you talk about it as well. So no one really wants to hear, oh, you've got to use this, it's so low in carbon, it's brilliant, it's really good for the planet, because they'll just think it's really expensive. So you just sell it to them as like a very standard thing, a prefab beam, essentially. Masonry walls, this sort of language, it's very accessible. So instead of glorifying it, because the whole point we're trying to make is that, with the exception of one or two projects that were a bit indulgent, the rest of them is just as basic and cheap as possible. Like, we have to survive in a world which, well, we do anyway, we get all types of clients that just don't really give a shit about what it looks like. They just want it cheap. And we have to work with that. So that's where we're coming from. That's why we're talking about bricks and, accessible things off the shelf, like, nothing lovely and bespoke and wonderful. But does that answer your question?
Yeah.
All right.
Thank you. I was having a read through some of your slides when you were talking about the carbon impact of your buildings. I was quite interested to see that you were linking some of the materials with the carbon impact. I was wondering how much you look at the CO2 in terms of CO2 versus CO2e when you're looking at the carbon readings and when you're trying to determine how impactful that material is in terms of harmful or good for the environment.
So that list at the beginning, it's like 100 slides back. Okay, whilst you do that. The list at the beginning, it's color-coded. And the purpose of it doing that is because, like, God, I think I'm going to pass that. The purpose of us doing that is because we're very aware that you can't make everything from timber and stone, and like you know, you have cables or conduits, or you can't make that from timber, can you? Or a plug socket. This is probably good enough. Actually, back before, and again. Sorry. Yeah, here you go. You know, some of this stuff you can't swap out. You just can't. Foundations in the ground, although you can use a bit of stone sometimes like it's a multi-level basement, or it just makes sense to use other materials. You have to. So you have to go a bit further up. But the reason it's color-coded is because we sort of treat it like if we walk around the supermarket, you'll see labels on every product you buy. So it's either like high in fat or low in fat or something. So if you're like Will, you might be kale, broccoli, all the green stuff. And if you're like Jordan, it might be sausages and chocolate. So you have to have a balance, basically. You can't just do one or the other, is our point. We're not, we're not blind to that. We're not like consciously blind. We're just saying, if it makes sense along the way to swap these things out, then you can. Now, in terms of how you're counting that, then, like, some people don't count the negative bit in timber. And what you need to do in that is ensure that your timber in your building is going to be reused afterwards. So you can legally include that in your planning permission into the section 106 as a condition. They have to do that, and that follows the building around forever. So they can't just demolish it. They have to reuse those timber elements, and that means that they won't just burn the timber and the CO2 goes back into the atmosphere. Sorry, the carbon goes back into the atmosphere. So that's how that goes into the minus element. So sometimes you'll see timber above, sometimes it's lower. And then some of these, vary slightly. Different types of stone, depending on where you get it. You've got to ship it further. But as an example, with a brick, a stone brick versus an actual brick, if you made a stone brick on Australia, you could ship it all the way here, and then ship it back again, and then ship it back again to here, and then it would be the same amount of carbon as your clay brick that you found down the road or something, just because of all the processes involved in that. And you can say that the energy going into that in the future, if it's all lovely renewable energy, then great, that starts to come down. But we're not in that world at the moment, so we're trying to work with what we've got. Hopefully in the future, lots of these things like steel manufacturing, brick, brick, you have to bake that a couple of times, a couple of 1,000 degrees. The energy is just tremendous for that. So at the moment, we're kind of doing what we're doing for that reason. So it might change in 15 years, but something we try and teach is that we're interested in architecture that's sort of emblematic of its time. So you can tell it's been designed at this moment in time. That's how it's expressing itself. That's how it's using its materials, available materials. And people have, I think, lost that ability slightly to read what is actually emblematic of this era. It's not, some like neoclassical thing applied to a building per se. It's something else, and it's still equally as expressive and rich. It just might be from a different palette of materials. So that's what we always try and challenge people to argue with us, So that.
Yeah, I guess to further the question, are you aiming to be carbon neutral or carbon negative, or are you trying to be as little? In terms of impact, are you trying to have as little impact as possible, or are you trying to aim for that carbon neutral or carbon negative?
I mean, negative, really. You can make the argument that if everyone was building the right way, timber with stone, for example, and the timber was responsibly sourced, so it was regrown, and you were locking that into the building, then actually the building industry would be a carbon sequestering industry. So it'd actually be taking carbon out of the atmosphere instead of pushing it out. But if you wander around, everything's like concrete, steel world. So it's obviously not at the moment. It's pushing it out there as one of the highest emitters of carbon in the world. So there is a thought experiment that you can do that if you build in the right way. It actually starts to sequester carbon and lower the carbon in the atmosphere. So it's actually like a positive. So you always aim for that, and then you have to choose your battles really as you go through a project. And also it's project by project basis. For example, timber in certain size buildings might not make sense because of fire reasons and things like that. So you've also got to listen to the requirements that go along the way. But that's why each project sort of evolves a little bit more, because you learn from all those mistakes, essentially.
Thank you.
That's all right.
I first of all wanted to say that, I found all the projects that you guys presented really cool. That pavilion that I think it's in Finchley, you guys said, I'm definitely going to be visiting that and using that as like a precedent at some point. I had a question. I wanted to know, are there any projects where your primary focus was pushing the boundary of what you can do with stone and timber in terms of how sustainable you can design? Because you've mentioned that there are some projects where you were a bit more indulgent in terms of like how you utilize the budget. And I was sort of curious, have you explored the potential of using, for example, stone as a structural element alongside, like, in addition to the facade, and timber as a structural element? And if so, what were your findings from that?
Yeah.
I think we always try to use stone and timber as the core structure of everything. I think like you said, the Stone Demonstrator is probably the epitome of our research at the moment into what we think is the most sustainable way to construct, most simple, basic, sustainable way to construct what we already typically see today. And any, I guess, architectural delights or anything else on top of that is left up to the architect. But this, for us, was not to house anyone, but to produce an example of exactly that, exactly what you're asking. How do we build just purely sustainably today with these materials? And this is essentially it. I hope that answers your question.
Yeah, thank you.
Yeah, I think part of that, though, is understanding what you're building, because this is, stone is still bad, because you still have to core it, and there's steel in there and stuff. So if you can build it from timber, and that timber is actually from a good, responsibly sourced woodland, then great. But you can build badly from timber, and, timber still can emit carbon. It's not like the ultimate product, and also is limited by what you're trying to do with it as well, because a building of this scale it would be fine in timber. But this is a demonstration of, if you're doing like a 20-story tower, 50-story tower, this is how you can build it very easily. Or most of the buildings around London, like 7-8-story apartments, you can build like that, and it meets all the relevant regulations. So it's kind of, it depends what you're building, basically. But stone is only there if timber can't do the job for whatever reason. Or it's not available, or whatever it is. But it's like, look locally first, and then you just use a material that's right for what you need it to do. Like you wouldn't build like a sort of timber basement, for example, and all these things. So it's kind of up to you to play with. This is not for us as well. This is like for you all to play with, and that's the biggest part of it. That although we do the research and make it come together, it's for other people then to kind of pick up and play with, especially students, to kind of really see what hundreds of architecture students want to play with if it was like that. Yeah, sorry, I just want to add that.
Thank you.
What was the process of the aesthetic arrangement of the stone facades? Did you know exactly what pattern and colour and texture was going to come in, or once it arrived, did you then have to rejig the puzzle? And also, if that's the case, like, when in the design process did these materials arrive? Was it pre-planning or post-planning? And also, like, what was the digital interface like in transferring the exact shape and size and all the quirkiness of the materials? How did you get that into a Revit model? Long question, sorry.
You did Finchley.
For Finchley, so I think there's a few questions there, but for planning, we made it very clear from the start that we're not going to prescribe this finish here, this finish here. We're telling them that these are the 3 or 4 types of finishes that we're going to have, and they're going to be spread all over the facade, almost out of our control as they arrive on site. But between the design team, the structural engineer, and the stonemasons, we would annotate all of our drawings for areas of tolerance, essentially. So this is a typical lintel. So where there's areas where it's fixed below, there's a 0 tolerance for finish or split face. And then where this becomes, for example, on this outer face, you're free to have a plus or minus. We set up, I think it was a plus or minus of 50 or 100 mil. So it depends where it sits on the building. Around the core, we had to have 0 tolerance because of fire regs. So we had to prescribe exactly what dimension these would be. And the structural engineer would set out the minimum thicknesses, and then the finish would be anything on top of that. So structurally, for example, this block above, there's some quite elaborate finishes on a couple of the blocks. And so the structural engineer would have modelled this as a regular rectangle, and essentially any finish is coordinated between the stonemasons before it arrives on site. And we was kind of happy with the way that the finishes fall. I guess in some cases, if we go back to Clerkenwell, I don't know if you want to speak on that, but a lesson that we learned at Clerkenwell is, where has it gone? Have we got a facade? Yeah. So over time, pieces get saturated between 4 cycles, and they might split and fall off. And so being able to coordinate those so that they're not facing on a main road or brushed and finished properly before they arrive on site is something to be aware of. But yeah, we're kind of happy with wherever the finish lands, essentially.
You get a choice, 180 degrees. When you arrive to site, you can do. Sorry. When you arrive to site, you can rotate it if you want, just so it's not like a line of the same finish. So you get a bit of play, but yeah, not everything's completely prescribed. So yeah, so it's kind of up to you. You know, you stand there and think, this one, or you know, it's sort of subtle, but I think that's it.
Yeah, okay.
Oh no, there's a. Sorry. Sorry.
So my question is regarding your post-tension beams and how I've noticed that you have a lot of elements that are metal exposed to the elements, that they're not inside or within the envelope of the building. And I'm wondering what is not health and safety, but the caution you have to take to prevent it from corroding or being damaged by these elements.
It depends if you want to expose it or not, really. You need to get to the end of those plates anyway, like in a post-tension concrete beam. You need to get to the end of the plates if you need to tighten it or test it for whatever reason. So if you bury it behind a facade, if you want to, you might have a little plate there, something that indicates, and again adds sort of variation to the facade. If you want to keep it exposed, like with any metal that's exposed, there's millions of buildings with exposed metal on the outside. It's, first of all, depending on what you want to use. I mean, it's likely to be steel, and then you just galvanize it, or it's stainless steel, and that's already pre-finished and weatherproof. If it's galvanized, then it's galvanized after it's been cut and everything, and then you just need to then finish it however you want, or you might leave it as galvanized. Yeah, and that's as simple as that, right? I mean, people use exposed steel in buildings everywhere. I mean, walk around London, you'll see stuff, bridges, all of these things. So as long as you make sure the steel itself is either galvanized or specified in that way, like it's stainless, then you can kind of finish that, paint that with whatever you want afterwards. So it's up to you. But you can leave it all exposed if you really want. The only issue is then breaking that slab so cold air doesn't come through, like a thermal break, depending on how you want to do it, basically. Yeah. Do you want to add anything?
And then, sorry, final thing.
Oh, yeah.
I've noticed that it's quite blocky, the stones, and I was wondering why you didn't go for more of like a Georgian lintel shape for the stones, to kind of also have the shape help you with transferring the load.
Well, I mean, a lot of these are just trying to replace standard elements. So a standard lintel is what's easy for a bricklayer, doing like a Barrett home thing. So we're starting there. What makes sense to span that gap? If we said we want to replace all the materials you want to do on your Barrett homes, however many millions of bricks that are built in the UK every year or used, but we want to use Georgian headers above our windows, then that's just an excuse for someone to be like, that's going to be at least triple the price. We haven't done that for millennia. Let's not do that anymore. So it's, of course you can do it because the technology exists, but it's about accessibility and simplicity as well. Like cutting those bricks to those angles, again, is like another specialist thing. And like I was saying before, we're interested in like the beginning at the very bottom of the market and working up from there, because we think that's how you should try and convince everybody. If you start here at the top, and there's all this part which is going to disagree with you and that stuff. So you can do it, of course you can. You can do whatever you like. And I think the interesting thing is if you build a building really rudimentary technology and it's very cheap and very basic, then yeah, you have opportunity to include these details which are a bit more indulgent and perhaps not fully necessary, but you just want to do because there's a building you want to reference, or there's another narrative of your project or something. But so it's about balance, I think, on those things. They only built like that because that was the technology at the time, They would arrange the bricks in that way, again, arch bricks in that way. So it's about telling the story of the technology that you have available to you now, essentially.
Great, thank you.
Yeah, sorry. Say, you all right?
Will you take one more question?
I didn't know you went here. Thanks for coming. Sorry.
Sorry about that. So the question is about the... Oh, sorry. I had a question about carving. How much you can carve, how deep you can carve, and what's the limitation for the carving? Is it like marble, or is it completely different? Does it need human force?
You mean quarrying?
Carving.
Oh, well, you've done lots of carving.
Sorry, what was the question? How
So what's the limitation with the carvings? Like how much you can carve deep in, or is it like marble that you have some human force with it? Is there any machine that carves it, or?
I mean, how thin you can go?
Yeah.
Yeah. Well, we typically, I guess the simple rule that we've been using is 2/3 of material left. So 1/3 deep. In a simple wall, you're allowed deviation of a third of material. In terms of how you do it, it completely depends on what you're trying to achieve we use both. We use CNC quite a lot when there's repetitive, the same cuts to make, or a type of precision that isn't achievable by hand. But we do have a lot of, for example, stone masonry company will often finish a lot of their blocks in hand. So when there's occasionally a split face, they'll do this by hand. A bunch of these are finished by hammer and chisel. But yeah, does that answer your question?
Yeah, it does.
There's like a bit of fat on the outside of a column. Like your engineer will say, this is what you need. You need like 300 by 300 or whatever. So you get it from the stonemason. As long as you don't go smaller than that, then it's fine. And as long as you don't go so much more that your foundations won't take it because you've added so much more stone, then you can do whatever you want. Different stone is easier to work. Like limestone's quite soft, isn't it? And granite's really hard. Basalt's sort of in the middle. So yeah, you can like work at different types of stone. They all do it by hand though, don't they? Like old school chisel or like a mechanical chisel and things like that. So it's very, very simple in that sense. We experimented with some CNC routing before, like you said. I forgot to put a picture of it on, but the interesting thing for us, we just come back from a trip with some students and to Albania and went to a stone quarry there, and they're still doing lots of sort of neoclassical Doric columns and things like that. But before they get tooled, they're CNC'd. And you get these really interesting like lines on where the CNC machine has gone at it, the tool has gone at it. And for us, that's quite interesting because I think that's more telling of the age that you're in at the moment, that a machine can do that, than trying to make it look like some perfect hand-chiseled thing. So again, in terms of student work, like the moment those two meet, the working by hand or working by machine, there's some interesting dialogue that occurs, I think. So we've done bits and bobs like that, but yeah, you can, like I said, we're trying to go in at the kind of low end, but there are some people who do want that kind of intricate carving and stuff. It just depends how you want to go about it. But yeah, structurally, you just don't go any smaller.
Thank you.
Yeah.
Thank you.
Well, look, thank you both so much. That was a fantastic talk. And yeah, I was struck by what you said at the beginning about architects and the way that we all just suck up all this ridiculous building technology, layers of things and all this nonsense. I mean, so it's just nice to see someone else doing something differently. And also you're thinking about the cost and the logistics and all the rest of it. So that's a real inspiration for us. So thank you. And we've had Steve Webb come and talk about how this works structurally a couple of times. But it's really nice to have both of you talk about how you're dealing with it as architects, because it's a bit different, which is really useful. So thank you very much.
Well, interestingly, it's like it's not different. We're like kind of like going backwards in time. Ideally, to how we used to build, and how we as architects used to train as well, by understanding these basics and how these materials come together and where materials come from. So we're kind of going backwards in a good way, though, I think, past all the crap of the last 10 years or so, 20 years. So, yeah, for students, I think that's a good way of looking at it, potentially.
Well, thanks very much. Thank you.
Cheers. Thanks. Thank you very much.